Okay, this is a BC Courses 2.2 supplement, and if you're in the AB course, this comes from the 3.1 supplement. So before you do that actual lesson, I want to look at these types of functions, because we haven't really seen how to do the derivatives of these types of functions. Scary. Now, the above three functions have this common feature that they are actually combinations of simpler functions. So I'd like us to see if we can identify those functions first of all. So if you look at A, we've got the square root of x squared minus x plus 2. Well, we get this function by starting with what function? Well, you probably start with the stuff inside the square root. Yep. And then you're going to apply the square root to the result. Okay? See if you can do part B and C yourself now. So the cube root of x plus 4 is the result of starting with the function. You guessed it, x plus 4. And then applying the cube root function to the result. And the last one here, x squared plus 3x minus 100, all raised to the power of 25. Yep, starting with the function x squared plus 3x minus 100, then applying the function blah 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 to the power of 25. Now, do you remember what these functions were called from your pre-calculus 12 days? Yeah, functions that are put together this way using simpler functions are called composite functions. Okay? Remember that stuff, the f of g of x? Or g of f of x? Yeah, that's what we're doing today. We're trying to figure out how to differentiate these composite functions. Okay? So, I'd like to just take a look at these two, and I want to differentiate these two different ways. And then hopefully from these two examples, you and I can come up with a nice kind of procedure or formula to find the derivative of composite functions. So the first way will be expand and simplify. Okay, if we do that, notice x cubed squared just becomes x to the power of 6. I can quickly find the derivative using power rule, 6x to the power of 5. Done. Okay, the other way. And I'm actually just going to call it the other way right now. There's no name for this way. So this one I like to just look at the function. How about looking at something squared? If I were to take something, let's call that x, and square it, you'd probably think that the derivative would be 2 times that something, right? Bring the 2 down to the front, reduce the exponent by 1 using power rule. Great. If I did that, my answer was 2x cubed. But from the first method, we know our answer is 6x to the power of 5. So my question is, what's missing? What must I multiply 2x cubed by to give me the result of 6x to the power of 5? 2 times, right? 3 is 6. X cubed times x squared seems to be 6x to the power of 5. Okay, so what's missing here is this 3x squared. Okay. Let's try the same thing with example number 2. Okay. Method 1, expand and simplify. Y equals x to the power of 15. Derivative using power rule, 15 times x to the power of 14. Good. Now let's try the other way. This time, once again, keeping the bracket x to the power of 5 cubed, thinking about blah 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 cubed, taking its derivative as a power 3 times blah 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 squared, probably. And if I did this and I were to simplify, that's the same thing as 3 times x to the 10. So once again, what am I missing to get 15x to the power of 14? And if you're thinking I'm missing a factor of 5 and an x to the power of 4, you are definitely correct. Now, I want you to look closely. The thing that I'm missing, how are those answers related to the other things that I just highlighted in yellow? If you can say that the thing that is missing seems to be the derivative of the inside function, give yourself a pat on the back, because that's what I see too. So ultimately here, if you think about it, using this other way, I can just pretend that it's like a power rule, right? Ignore the inside function, do the power rule, or take the derivative of the outside function, and then stick the inside function back in, and then the missing part, or the extra little bit, seems to be the derivative of the inside function. So understanding that, you've actually understood the chain rule. So the chain rule is for composite functions, okay? So how to take the derivative of composite functions. So if I have a function h of x and it's a composite function, it's made up of two separate functions, f of g of x, then the derivative of h is equal to, now look at this, f prime of g of x. So this here represents the derivative, and please write this down, of the outside function. Okay, but look, it's a g of x in there, so derivative of the outside function evaluated at the inside function. And that's what we all do, but we're forgetting what's missing, or that extra little bit. And that extra little bit is this g prime of x. It's the derivative of the inside function. So chain rule says take the derivative of the outside function, evaluate at the inside function, and then don't forget the extra little bit, or the hook, of the derivative of the inside function. Okay? And that's the definition of chain rule. Now, if calculus was so easy, that'd be great, but it's not. So there's another way of thinking about taking derivatives of composite functions. This time I'm going to use this notation du dx, which really means the rate of change of some function u with respect to x. Then I have something else, dy du, the rate of change of some function y with respect to something else called u. And then the rate of change of y with respect to x, dy dx. Now, think about this. If u changes twice as fast as x, that's like this, and y changes 3 times as fast as u, that's this, then it's reasonable to assume that y changes how many times as fast as x? And if you think 2 times as fast, then 3 times as fast. Think about what I'm asking you here. dy dx, that's equal to what? dy du, maybe multiplied by du dx. Think about that? Yeah, because it becomes just dy dx. So you're just going to multiply this twice, 3 times, 2 times 3. You got it, 6 times. So another way of thinking about chain rule is to use this form, where if I take the derivative of y with respect to x, that's the same thing as me taking the derivative of y with respect to u. So this new function called u multiplied by du dx, the derivative of u with respect to x. Okay? So let me show you now example 1 using both forms, and then at the end I want you to decide which one you like better. I definitely have a preference. I've seen most students prefer one or the other, but I of course will show you both. Okay? So looking at this example, find the derivative of h of x, and it's equal to x squared plus 5 to the power 4 using both forms of the chain rule. So the one we learned on the previous page, remember, the derivative of the outside function evaluated at the inside function multiplied by the extra little bit of the derivative of the inside function. So here we go. H prime of x would be, so which one's the outside, which one's the inside? That's the most important part. hopefully you can see that x squared plus 5 is the inside function, and the outside portion would be blah 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 to the power of 4. So take the derivative of the outside function, 4 blah 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 to the power of 3. Evaluate it at the inside function, so put it inside the bracket x squared plus 5. And then please multiply by the derivative of the inside function, g prime of x, that's an extra factor of 2x. And if you want to simplify this, the 4 times 2x gives you 8x. And we get x squared plus 5 to the power of 3. I don't want to expand out the cube function, so let's just leave it like this. Done. Okay. Now, how about this other method here, okay? The alternate form of the chain rule. So, dy dx, okay? The derivative of y, in this case we can call this h of x, y, as a function of x, is equal to the derivative of y with respect to u. Okay, so in this case, what you need to do is find something that equals to u. And the thing that you want to be equal to u is always the inside function. So in this case, u equals to x squared plus 5. And because of that now, you can then say y is equal to not x squared plus 5 to the power of 4, but u to the power of 4. Okay? Now, why does this help? Because this y equals u to the power of 4 will help us figure out dy du. Because the derivative of y with respect to u, dy du, would be 4u cubed using the power rule. Then u equals x squared plus 5 will help us find du dx, the derivative of u with respect to x. Using the power rule, once again, this is 2x. So knowing these two components, now can you figure out dy dx? Well, dy dx is just those two components multiplied together, dy du, which is 4u cubed, times du dx, which is just 2x. Can you see how this here pretty much resembles that over there? Right? 4u cubed times 2x. But we can't leave our answer with u because we started with x. So now at this stage, resubstitute. And once you've done that, you'll find the answer, dy dx, 4 bracket x squared plus 5 to the power of 3 times 2x, and then like what we did on the left hand side of this example, we just multiplied the 4 and 2x, and look and behold, same thing. Okay, now I'll let you decide which one you like. Tell me when you get back to class or write to Teams, but I'm curious as to which method you like. Alternate form, the one with you, or the definition form using this outside inside function stuff. Alright, now you're ready to watch the lesson 2.2 video, so go ahead and do that and then get to work.